there, I'd encourage you to do so, to enroll in it, because it's pretty good information that would surprise you on the efficiency of air movement and how poorly, even though we think we're doing a good job, we may not be doing as good as we think we are. And Dave and Gary have done a lot of research on this and put together some really good course. Actually, it's probably the best course that Tech has ever put on. Anyway, tonight what they're going to do is just a brief synopsis and give you information on what you can do to analyze an existing system and determine how much air that system can move and how well it's moving it. So with that, I'll give the floor to David and Gary. And
sounds good.
We're not exactly sure who's to talk. We've been playing around with this for a lot of years, and since September, Gary was able to find a really nice house that would serve as an example. But the object of the game tonight is if you walk into an existing house, and the house is the basement's been boarded up right to the appliance, you have absolutely no idea what's inside the house. You probably don't know how much air that system is moving, and you want to put in a new appliance, and you want to try to take some of the risk of the change-out. That was a motivator for this. So in terms of a part of basics, you could say that it's maybe 5 to 10% of what the basics course is about. We're just going to cherry pick it. I'd like to thank Charles also, because he got me going on this years ago with a sample house, and I've been out a few with him and learned a heck of a lot working with him as well. But Gary's put a hell of a lot of time and effort into that, even as late as this afternoon getting ready for this tonight. So the two of us are just going to go through a sequence of 28 slides to try to give you a little idea how easy it is for you to take the risk out of the changeout. We've also generated over the period of the last little while and gone over and over and over again a pre-changeout form. If you choose to fill it out with the furnace example that we got tonight, fine. If you choose to use it yourself, it's the best way that we can put down in simple forms what you need to know to answer the question. And we're going to fill that form out on this overhead here, and we're going to use this model here for just a couple of very simple things to show you what we're talking about. But we're just going to walk through 28 slides right now and show you the process. You're walking into a customer's house. What do? You're trying to assess the existing system.
just a side note, I forgot to mention, we've tried to create in the interest of time and keeping everybody here as long as possible, we try to keep the questions down to a minimum until the end. If they're really pressing questions, or if David needs you to ask questions, he'll ask. But we try to keep the questions to the end, and I'm sure Gary and David won't mind hanging around for a bit if we get questions afterwards for those that are interested.
You can have your remote if you want to.
Okay.
Whether you control it. Down one. Down one.
Down one.
Still down one. On. Down.
Amazing.
The down one.
The down one.
Down one.
Good. I figure it's going to be a little easier for you if we know what we're talking about. So Gary arranged this as Chris and Sandy's house. We drove up there and began working. And it was a nice, easy basement, which made it easy for us to find things out. But this is the house which we're going to focus your attention on in the next few minutes. The problem is how to determine how large a heat pump or air conditioner can be installed in an existing duct system. That's the question before us. In this case, it was easy because it was a big, huge open basement. You could see everything. In many, many cases, that will not be something that you're going to have, and you're going to have to make a judgment call, and you're not going to have a chance to see a thing. The method used to attain existing system volume and pressure drop. Okay. Gary's got some new stuff this afternoon that I haven't even seen yet.
That's right, yeah.
He's been working hard on it all day while I've been sitting in a code meeting. Determine the rate of flow of the system. Is this the one that was the key one?
Gary, did you bring any more?
No, that's all we copied. We got 25 sheets.
Too many people
Those
here.
of you that have two, you might need to share.
Okay.
This is the route we were going to take.
That's correct, yeah.
Good. Okay.
Go to copiers through
The key thing is we want to know the CFM of the system you've got. Because really, when you're changing out a furnace, you're going to have to decide, or a heat pump, you're going to have to decide how many BTUs you want. But just as importantly, will the ductwork in that house right now handle that new appliance? And this is something we've been really remiss in this industry.
Maybe, is there more forms that guys can get online, or should we do that?
I'm a Neanderthal. If anyone wants, how do we deal with this?
You can email it to me and I can email it to them.
Okay, that's a good idea, because this is,
Anyone that wants a
That's a good
form and
answer.
didn't get one, just let Catherine know. And
we'll make sure tomorrow Catherine gets a copy of this sheet and you can print out as many as you want. Thank you, Catherine. And Jerry, thank you for getting the pens for this tonight. Those dropped, thank you. Okay, we want to find out the CFM. We got to measure a temperature rise, gas input, estimate the appliance operating efficiency, and we're going to get the CFM. And the beauty of this is you're going to get a very, very accurate answer. It's probably one of the most accurate ways you can get of the actual CFM that's circulating. And the only thing you need to have is an appliance that's actually still working. If it's cracked, Mickey Mouse it to work, you can do that, that's your racket. But you've got to actually have the appliance working that way. It seems Charles and I did that once. We had flames coming up about 6 feet off the front of the appliance when we Mickey Moused it. It was fun, wasn't it? Okay, there are 3 methods, and we're going to get into this one. But you could measure the velocity in the ductwork. But residentially, the duct is generally quite small lengths. You can't get in with a pitot tube and measure it accurately, so it's not really a good, easy way to go. You can measure the pressure drop on the return and the supply and go to the manufacturer's equipment, and from that you could actually get the CFM. But if it's a 25-year-old appliance, you're probably not going to have that information available to you. This is the only thing that we've found that works, that's accurate and fast for you to get the answer that you so desperately need when you're changing that appliance out. This is just a garage, a basement view of the furnace we focused on. It was kind of interesting too. Anyway, we'll get into that. There were 2 variables in this that were very, very important to us. We tried it with a no filter, a regular 1-inch mesh, which is really a rock catcher version, and a pleat. And you really have to look carefully at this because each of these filters, the appliance performed quite differently. When this guy went in there, all of a sudden the furnace was running in a sweet spot of its temperature rise. This went up with a clean filter to within 1 degree of the upper limit of the recommended 40 to 70 degree rise of the appliance. And as Merv Terrio says, there's a double whammy here. These filters are rated for uniform velocity across the face, but when you put them at the bottom of the drop elbow, you're putting the filter in a position that is horribly adverse. It not only doesn't filter properly, but your pressure drops can be 2 or 3 times clean what that filter brochure says the pressure drop should be. We'll get into that in a minute too. Side view of the furnace, a little bit unusual. There was only 1 plenum takeoff as opposed to 2, but that again just gives you some perspective of what we're looking at. And it had a kind of an interesting fitting across the basement ceiling, just about 6-8 feet from the furnace. There was really a rather nice, what would you call it? Almost a pair of pants, an offset pair of pants. And it actually flowed very, very nicely. The pressure on the supply system was very, very, very low, quite surprisingly low. First of all, you got to find the gas meter. That's Gary looking for it. He found it. English meter. Okay.
That's easy.
First thing we had to do is set back the water tank, because that was the other gas load that we couldn't control. Clock the meter. You go to the tables, and we knew that there was exactly 100 seconds for a 2 cubic foot dial. So you look over here at 100 seconds, we know there was exactly 72,000 going into this appliance.
David, if you want, on the upper right is the little LED.
Thank you.
The LED area.
Yeah, it's amazing technology. 72,000. And we're really, really, really confident in that 72,000. Billing meters are a really accurate way to know your input. So we have absolutely no confidence, no lack of confidence in knowing what the input to the appliance was. Next, what we've got to do is we've got to take a temperature rise. You guys probably have a lot better instruments than we do, but you just basically take 2. A return and supply planet pressure, temperature rise. And that's all you need to do. So what we did on this form here, to give you just a bit of an idea, we clocked the meter, and we can actually fill this in right now, but we clocked the meter, and we know the input. From the gas table there, we know exactly how much BTU input. There was 72,000. The only error that we build into this thing is there's a little bit of uncertainty in what the steady state efficiency are, and if you're not going in there with a gas, what is it called, an analyzer? Combustion analyzer, thank you. Then you can make some reasonable assumptions. If it's a standard with a draft hood or a mid, your steady state efficiency, which is what we're doing for this test, is probably around 80%. If it's condensing, it's probably around 90%. You're going to get awful doggone close by using these numbers. So this was a mid, so we're sitting at 80%. So if I was to fill out this chart.
Now, Dave, we might want to mention right now the temperature rise issue.
Very good point. This appliance was rated at 40 to 70. In fact, why don't we just fill this in right now? 72,000. Yeah. So we had 100 seconds. And it was 2 cubic foot dial. And that was a total input of 72,000. Our steady state efficiency was 80% because we didn't do anything further to get that. So what we're going to have to do is get our supply air plenum, our return air plenum, get a temperature rise, and then we'll get BTU's output.
No, it's your form. We get BTU's output right now, Dave.
Yeah, what's the answer for that?
56? I don't know.
56? Okay, so we're getting roughly 57,000 into the house. I think we got a pretty fair assumption on this. Okay, now temperature rise. Gary's measuring the temperature rise at return. When we started horsing out of this house, it was about 65. By the time we finished screwing around for 2 hours, we had the house to about 80. They're quite tolerant homeowners. Yeah. But once you get good at this business, you only have to do this for 2 or 3 minutes, and you get a good solid answer. We just screwed around a lot. And you got a temperature rise on the supply side. Just, of course, far enough away from the heat exchanger of the furnace that the radiant effects are not causing an artificial high reading on your supply plenum temperatures. Or if you got some nice digital gauges or you got some nice differentials, you can do that all at once. And what we did is we got a temperature rise. I'm going to get into this because this is highly dependent upon the filter. So when you play this game, you've got to know the state of the filter. If it's loaded all up, you're going to run the machine at high limit.
If we backtrack 1 sec, Dave.
Yeah.
The point I was making here with regards to the 80% is that manufacturers rate their furnaces at the minimum temperature drop. They always want to maximize the published efficiencies of their equipment. So if you have a furnace that's rated at 94% efficiency, assume that furnace was rated running with a 30 or 40 degree temperature rise. Now, in practice, it's really hard to find a furnace that's installed with that much air flowing through it, so you only get a 30 or 40 degree temperature rise. The net result is you're running at higher temperature rises. Henceforth, the flue gases are also a higher temperature, and the efficiency is down. So just keep that in the back of your mind when you're making an assumption as to what the functional and actual operating efficiency of the equipment is going to be. If you're low in the temperature rise, you might be able to bump up the 90 degree or 90% number up to 92 or 93. If you're high, just err a little bit on the lower side.
We spent a bit of time with Clark Purvis on this question because his course used to be a manufacturer. Now he's wholesaling for Echo and Kelowna. And we figured that the change within your temperature rise is probably good for 2, 3, 4% on efficiency. So if you're crowding the high end, you're probably throwing away 3 or 4%. If you're crowding the low end, you're going to be saving that. And what he found was really interesting. When he got right into his equipment catalogs very, very carefully, he found that the efficiencies were actually done at temperature rises were lower than the lowest recommended limit of its own manufacturer. When you're playing games with government, you pull all the stunts you can pull. Now, the other thing that we want to do, and we'll get into this temperature rise difference here in just a minute. The other thing you have to know is exactly what pressure this system is running against, because we've been able to, with this Actually, does anyone want to work out the CFM? We should do that right now because we haven't. No, we don't. We don't have those numbers here in front of us because they're farther on the slideshow, aren't they? Okay, we'll get to that in just a minute. We'll fill this out so we can actually get the CFM. Okay. We then have to measure some pressures. And one of the things that I like about a magnehelic gauge is they're relatively inexpensive. You can drop them off a ladder. They're a pretty forgiving instrument. Some of you guys may have digitals. Doesn't matter what you use. You could even use, a magnehelic, or you can use a manometer. It's just these puke oil all over your toolbox, or pain in the ass. But the fact of life is you don't have to spend a lot of money on a digital manometer. You can get very, very accurate results with something that costs you $100. The skill is in using it, not how much money you pay for the tool. Okay, this is where it starts to get interesting. This is the base case. This had the standard filter, that mesh filter we talked about, and this is the information that you want. We had 72,000 in, 80% assumed, we had 57,600 coming out. Our allowable was 40 to 70 degree rise, and we had a temperature rise in this situation of 48. And on that particular thing, we didn't actually fill these out, but the net result is we have a 48 degree rise. And if we work through this formula of BTUs of 57,600 divided by 1.1 times the 48, we got 1,120 CFM. That's the base case.
And we're probably within plus or minus 3% of that number in real life.
Really, really accurate and fast. As fast as we can talk about it, we were able to do it. Okay. Now, the next thing is you have to, with this, take a look at, well, how much pressure am I overcoming to develop this degree of circulation? It's a sweet spot for the furnace. It's running 40 to 70. We got a clean filter in there. It's running 48. I mean, it's a pretty nice place for that furnace to run. Okay, this will blow you away. If we measured the return air in the horizontal, we got almost nothing, 0.5. Here, 0.15. This crap fitting cost us 0.1 of an inch. That's a third of the entire quality first external allowance of 0.3. Here and here were roughly the same because this is a straight section of ducts, so you'd imagine that there's no turbulence effects. You're getting good results. I'd rather punch a hole here at eye level or go down here 2/3 of the distance, which is the theoretically most accurate point because you're away from the disturbance created up here. But if you go into the appliance, you find out that you've got minus 0.3 of an inch in there because the combined effect of the filter, the horrible environment we put the filter in where all the air is flying through the bottom section of it here, and the ugly shape of this sharp throat fitting. So we have consumed, in this system, the entire quality first pressure drop allowance just on the return side. On the supply side, we go up in this plenum here, not too close to the top because you get a bit of high pressure bounce at the top. Over here it's so turbulent it's bad. 2/3 of the way up we took a little wee hole and we got 0.13. What this means then is this appliance is drawing on approximately 0.03 here. Additive to this, the external static pressure this appliance is overcoming to move its 1,120 CFM is the sum of the two numbers, and it's 0.43. So that's the starting point. The interesting thing that comes from this, too, is the motor current. This is an AC motor. In the standard configuration right now, we are running 4.8 amps on heating speed. Now, we took the filter out. What was the result? The flow, it came up a little bit, but not enough to really worry anything about. Our vacuum here then went from roughly 0.3 to roughly half of that. We have no filter in it at all. This didn't change much, and that's common sense because the volume through this didn't change much, so there's not going to be any greater pressure on the supply plenum as a result. So in other words, basically business as usual. Heaven help us though when we stuff the 1 inch in.
And this is the configuration we found the furnace when we got there. We found it with this 1 inch brand name pleated filter in the furnace.
Gary didn't want to tell me, but didn't want me to tell you, but I can't help spilling the beans. The sucker that was there before us partially closed the gas valve of this appliance, and derated it down to the numbers that we've given you here because he was running at limit and over limit when he had the thing running at its full input of 88,000, which was rated for. So when we said it was inputting 72,000, that's with the shutoff, the ball valve, closed about a third to drop the pressure to get the input to where that filter wouldn't be setting it off on high limit. Okay, yeah.
Is that code, David?
Ask Gary, he's an A-fitter. It's always fun going and investigating something, you know, because I won't go there. Okay. Well, with the filter, and it was a good filter, like Merv Terrio is a real believer in pleat filters, and I support it. This is a 40% or thereabouts filter, brand name, 1-inch pleat, lots of surface area. But our 0.3 now has doubled to 0.6. This here has come down because we're reducing the circulated volume. Instead of 1100 CFM and something like 30, we're down to a little bit under 800. And look at what our external static pressure is now. We're sitting at 0.7 instead of whatever it was before. A substantial increase. And you can see now, we're at the point right now, this poor sucker with a clean filter is nudging a degree short of the upper range which this appliance should be running at. We're running 40 to 70, we're running at 69. So you're now running now at a point where you've lost efficiency, you've thrown it away, and you have no reserve as that filter begins to load. Contrary to public opinion, the more dirt you put into a filter, the better it filters, but the price you pay is your temperature rise will go up and your efficiency goes into the toilet, and eventually end up short cycling because you're bumping up against your limit switch. So far so good?
And the current drop.
Oh yeah, this is a bargain. You save power. You drop 4.8 amps, you're now down to 3.9, so your motor loves it. Contrary to public opinion, you crack the filter, your power consumption AC motor goes down.
That's right. It's like an AC PSC motor. This is not true for an ECM motor. But it is true for PSC.
The exact opposite happens with an ECM, not because the ECM wants to consume more power. You program the thing to maintain CFM, and if you're going to be an idiot, it's going to consume power to please you. 3.9 amps. And by the way, this is not the inducer motor. This is just the blower motor. The inducer motor doesn't care about all this crap. Okay. But now this customer decides he wants to put a 3.5-ton heat pump in. The question is, can you do it? Well, let's say you want to put in something that's 1400 CFM, and right now you're running something around 1100. Well, you think, well, that's only 200 CM, 250 CFM more, no problem at all. But look more carefully. It ain't that simple. Will the new appliance work with the existing duct system? Now, the formula is not linear, so it's real simple, but don't be blurred into thinking it. Our original volume on the base case was 1100 and something. Our new volume was 1400. Remember, our existing pressure drop was on that
0.43.
0.43. What you want to find out is what will the new external pressure be, and is your new appliance capable of operating in that condition? So the original was 1120, the new one's 1400, 0.43 was our original external. You take these two numbers, 1400 over the 1120, but you have to square it because pressure and volume are not linear. You have to square it. So you double the pressure, you double the volume is 4 times the pressure. It's not a nice, easy thing. So you take this guy over this guy, you square it, multiply it times this, and you've now come to 0.67, which is getting, again, as we learned, too high for comfort in a residential system. You cannot put this type of external on. So you say to the customer, well, your ductwork's no damn good, it's not going to work. But let's say you want to survive, you want to save the sale, and you want to intelligently advise the customer what has to be done so you can put in this appliance and not end up cooking the compressor or high limiting if it's a combustion appliance. But this is not a good number. And I challenge you, and for fun, I bought one of these little gauges years and years ago, and it's fun poking around in returns and supplies. But remember, the appliance sees the sum of the return and the supply. It doesn't care whether all the pressure drops on the return or all of it's on the supply. It sees the two together. Although what I've learned in the last few years, in my opinion, the ideal forced air system is a hugely oversized return, and you want pressure on the supply side so you have control over where the air goes. But the appliance doesn't care. It looks at the sum of the two. That's all the appliance cares about. Static pressure is good for giving you control and supply. It's good for overcoming the resistance of a good filter. But don't waste static pressure being an idiot.
And remember too that that is with the fiberglass throwaway filter in there. You could not do it. If you put the pleated filter in, you'd be running like 1.1 inches static water flow, and then the fan, and I looked at the chart for that furnace, only puts out 650 CFM at 1.1 inches of static water flow. So you absolutely could not do it with a filter in there.
600 CFM is too close to that.
Yeah. So the filters are very important because modern day furnaces, we all want to sell air quality, just the buzzword, and we want to put a nice filter in there, but be aware of what you're putting in. 1-inch pleated filters have very high pressure drops.
I like to think of a furnace as it's a source of air power. And there's good parasites and bad parasites. A good parasite is a filter. A good parasite is a supply system that has a bit of pressure against it so you can control where it goes. But bad parasites is an undersized return and crap fittings on the return. They're bad parasites. Can we install a 3.5-ton heat pump system with a 1-inch throwaway with a plate with the return air duct with new return? Okay, well, that's the thing we want to look at right now. The system has to be designed to attain the minimum flow air delivery with a dirty filter. Yeah, you can't design for a clean filter, as we showed before, with a 69-degree temperature rise in a clean filter. That means you can only go for 1 more degree and you're off limit. And the whole life of that filter, you're throwing away heat up the chimney for lack of proper transfer.
Yeah, so the point is, when you're looking at your new equipment charts and you're looking for designed CFM, especially if you're using a PSC motor on it, you cannot design for the minimum CFM. You've got to design for several hundred CFM over that, so that when the filter gets dirty, your pressure drop rises, you're looking at a new higher pressure drop, and you have to be able to meet the required CFM at that new higher pressure drop, which is created by the dirty air filter. Otherwise, 3.5 years from now, you're going to be changing out a compressor in a heat pump or an air conditioner.
Merv uses the term in filters. It's called initial and final. Initial is the pressure drop of a clean filter. Final is the pressure drop when you blow the media right out of the frame. It's structurally adequate for that. Residential, you'll not get anywhere near close final pressures because you will be shutting down on high limit long before that. So look carefully at filters. They're good, but they do have challenges.
That's just a recap.
Oh, okay, so that's a replay.
Yeah.
Okay. To recap then, what we've done is we've determined the CFM. We've done that very accurately by temperature rise, gas input, assumed operating efficiency, and we got CFM. This just allows us to determine by pressure measurement whether we've got the ability to get more air through the system by measuring what's there. A couple things now about parasites, then I want to go into this and call it quits. This costs 0.1 of an inch in that one single fitting at the top of the drop. And this is the physics of what happens. When air from a return system, if it had been coming 2 directions, goes around this sharp edge, it triggers vortices here. And what Gary suggested, a 10-inch duct behaves at this point as though it's only 7 inches. So you threw away 30% of your duct area here because you triggered vortices and created a contracting effect right here. This is a very high drop fitting. 0.1 of an inch, a third of your entire allowance on a quality first system is consumed in one fitting. So if you have to knock down static, this is one place will pay huge dividends. The theoretical ideal would be to radius this as a true pair of pants. The less expensive route is to miter it, which is the quality first requirement.
No, it's 40, chamfer.
Chamfered is 45 degrees.
Yeah.
45 here, 45 there. This is something that was Gary supplied 7 years ago when we started this from, it's a Tuttle and Bailey catalog. It originated for some ASHRAE research when you put air in a duct, that's plexiglass, and you put little bubbles in it and you photograph it under strobe light condition. So this is real. This is not an artistic rendering of what happens in a regular drop elbow, in a regular heat pump or furnace system today. The air comes from upstairs in the drop. By the time it gets to the drop elbow, it's completely uniform velocity across the complete cross-section because it's had 5 or 6 feet of straight duct in which to straighten up from the damage you caused by a crap fitting at the top of the drop. What's happening here, however, is that the appliance drawing air into the cabinet, again, is creating vortices here. And this is a double whammy in that what's happening at this point right now is not only is this creating a huge pressure drop at this point, but what's happening is the only laminar air that, not laminar, but the only straight air you've got right now is going on here. What this means is this fitting here has cost you desperately in pressure drop, but even more importantly, the filter that you put in that so-called has a 0.1 or 0.2 static pressure drop initial, is running the air at 2 or 3 times the velocity through 1/3 of the area, so that the pressure drop initial is probably 2 or 3 times what you bought and paid for because you've misapplied the appliance. Here's a situation where this is desperately crying for turning veins through here, radius throat, or anything else that you know you should have done to make this thing work properly. Just to give you a quick answer here regarding measurement. This is a system here that's part of the basics model. And what we're doing here, just to give you an idea how easy it is to measure pressures, if you think of this as the uppermost part of your supply plenum above your furnace, you can punch a little wee pinhole. You don't have to put a big huge hole, just a pinhole. Just break the surface with your scratch hole or screw. You put this tube up to it, and this gauge right now is telling you exactly what your supply plenum pressure is. In this case here, we're just under 0.1 of an inch. Somewhat similar to what we had happen on this house that we went to visit. In this situation here, I think it'll blow you away. This is a very desirable place to measure the vacuum, the negative pressure in the return air compartment, because it is free of the disturbance here above. And right now we're sitting somewhere around 0.1 of an inch at this point. What's interesting, however, is if you go right inside the fan cabinet, this is 0.15, getting close to 0.2, and there is no filter in it. This is an absolutely brutal fitting to use, and it's a double whammy because it's sharp throat. This does not have a filter, it's worse with it. But then there's a system effect, and a system effect is the bullshit statement that a manufacturer uses to explain why you cannot get the air from his equipment that he's rated for, and it's an excuse to say that how you connected it has diminished its performance. Well, it's real. And I don't speak just as a manufacturer, but this is real. Just think for a moment what happens on a high-boy furnace. You bring your drop down, you make this horrible fitting, you put a filter there, but have you ever thought about which side of your double inlet blower the motor's on? If it's on the drop side, 2/3 of the air coming through that gets beat up on the corner, it goes through the filter, has to go all the way through the compartment, then back into the other side. These are called system effects because you're dealing with the less than desirable entrance to the appliance which that manufacturer's rated it for. Basically, the conclusion of the whole thing is in 1/10 of the time that Gary and I have gone over this, you could go through the process, measure these things, calculate your CFM, pressure drop, without seeing anything other than the supply plenum and the return, and everything else is invisible.
A lot of time, if we size it to quality first, the return air drop becomes so large that sometimes we even put the filter in the drop itself. Does that help?
I think the question Gus is asking, if you have a large enough return plenum area, putting the filter in the vertical section.
Yeah.
That's your question.
Yes. And
It's highly desirable because you're then putting the filter in a location that is approximately how the filter's been rated. If you have a filter that's this big, it's only giving you the efficiency and the pressure drop if you're allowing air to run uniformly through its full face area. So it's a highly desirable way to install a filter if you have the space. If you don't and you have to pull this down, this is crying for turning vanes and a radius throat, both from the saving of pressure drop, increasing the flow, and you'll probably get 2 or 3 times the service life out of your filter.
And unfortunately, radiusing the outer edge will do nothing for you.
We have data from ASHRAE and SMACNA that actually shows that radiusing the heel and not the throat can, in some cases, increase the pressure drop because you diminish the distance from here to the heel and therefore increase the velocity at the throat, creating more turbulence and more pressure drop. A radius heel looks good, but it ain't worth crap. That's
So what would be the minimum throat that you would recommend?
Bigger is better.
Bigger.
Yeah, that's the whole problem. That's the whole problem. See, the thing is, is if you're trying to do something with really, really small duct and higher velocity, you need a larger radius. If you've got an oversized duct, you can use shorter radius because your speeds are lower and the corner is easier for the air to turn.
Does it make any difference if the inside throat is curved or at a 45?
Oh, we actually got answers for that.
It really helps if it's 45. Helps a lot. Like 80% of the way there, I think, Terry.
Yeah, we can
Somewhere
actually give you an
around
answer.
there.
We spent $5,000 to answer that question, Terry. And I'll give you an example that I think will blow you away. What we did is we bought the latest ASHRAE CD called the loss coefficient. The problem is we couldn't read it. So we hired Don McAdam. He drew up the sketches and he put this all together, and I think it'll blow you away when you see the answer to Terry's question. If you have square throat, square heel, and it's 8 by 32 size, you got 50 feet of equivalent length is occurring in that one fitting. That's without adding the effect of an adverse use of the filter or the system effects of entering the furnace in less than uniform patterns. So this is looking at it purely from the point of view of that fitting without compounding effects. If you radius the heel, that 50 feet actually becomes 57 feet. We're splitting differences, but the fact is the pressure drop has become a little bit higher radiusing the heel. But to answer your question, however, this I think is better, and I have absolute convictions in where this research came from. It's the best the world has to offer for you. Radius the throat, leave a square heel on, you're down to 21 feet. But if you put turning vanes in this poor fitting, you're at 6 feet. Now, if you got all the money in the world and you're a nutcase, you can put a splitter in it, radius the throat, radius the heel, put 1 splitter and get 2 feet. If you want to put 3 splitters in it, you get down to 1 foot. That's not there because it's practical, but it shows you that 57 feet can be dropped to 1 foot if it's important to you in getting the airflow and knocking the pressure drop off for that new appliance. These are absolute, this has gone to the best information that ASHRAE and SMACNA can put together. So I stand behind these numbers with absolute conviction they're right.
But do not attempt to make a elbow with full radius turning vanes, because they have to be absolutely perfectly equidistant the whole way. And if you get it wrong, it'll be really bad.
This stuff isn't practical.
It'll break loose.
It's just here to show it for fun.
Yeah.
Did that answer your question, Terry?
Put that slide down, show us the 45 inside range.
Oh, thank you. That's where we're headed for this discussion. We did do a 45, didn't we?
It's right there. You got it, Dave.
Got it.
You
Which
got
one?
it.
This
Right
one?
there.
Yeah,
That one.
you got it.
Right there, you know.
Yeah. See, 29 feet's better than 50. And we actually played around with this on another fitting where we started making this 4-inch, 5-inch, 6-inch, 7-inch, 8-inch. The longer you go, the better it is. We'll just spend 1 second on that. We did it on long way fittings with a bunch of different, what do you call that in the middle of it? When you do this to a joint, what do you call that?
Chamfer. I don't know.
Chamfer? What's the correct sheet metal term for this? When you do this? Gotta be some smart guy here.
Cause more work.
Yeah.
Well, just to give an example, on the long way fitting, this was 74 feet, it became 65 feet, became 62. So as you start increasing the length of this chamfered part, you get to the point where it's not making much difference. But this definitely helps, because this square throat, square heel on a long way, I think, was 75 feet. Like, it's just absolutely bizarre. Yeah. If you take the long way fitting, it's worse than the short way. But this is 70 feet for this being mitered. So if you're going across the basement ceiling, you're turning a right angle turn with sharp throat, sharp heel to dodge the stairways, you're paying 70 feet, which is the length of the friggin' house. All in one fitting. And if you put two back to back, it's a lot worse than 1 and 1 makes 3 situation. So.
And look at the short way radius heel there, David.
Oops, this one? 83 feet. It's a lot worse than this, you can see. Everything, guys, is in the throat. Don't let anyone fool you. And by the way, anyone who says that a return air system performs differently than supply air system is full of it. Our air pressure right now, we're running at 400 inches of water column. If you run the return at -1/4 from 400, or the supply 1/4 over 400, the air doesn't know the difference. The density doesn't change. It doesn't matter whether you're pulling air through that fitting or pushing air through the fitting. The pressure drops remain absolutely unchanged. It doesn't matter how you do it. So the rules of supply are exactly the same as the rules of return. The shape of the fitting is critical. These, by the way, were all done at 500 feet a minute and 1,000. And quality first is sitting between the two on our main trunk ducts. But you can see it doesn't make a hell of a lot of difference one way or the other, whether you got this sitting here at 61 or 70. It's gross in both cases. But if you slow things down again, your effective lengths come down a bit. That's the whole story. Any further questions?
I don't like. I'm wondering, what if you put your filter, a cleavage filter, across here?
You know, I was thinking about that, Terry.
It'd probably help.
Would that act as a turning vane?
No, but it'd slow the air down a little bit for it, and so the effect around the inner radius wouldn't be as great.
Have you ever thought why Honeywell has a mesh filter in front of their electronics? It's not really you're trying to filter, because that mesh is coarse as hell, has no effect. Do you know what it does? By putting a pressure drop right across here, it's actually forcing the velocity to slow down here and more uniformly to deliver across the full face of the electronics and do a better job. That's the prime reasons why it's there. This is an ugly situation to be putting a filter of any type unless you put a turning vane in front of it. And of course the cheap answer, like I'd come up with, well, this will only make the bottom of the filter dirty 6 months, 2 years. A week later and turn around and put it upside down. But don't go there, guys. By the way, don't vacuum out these filters either. The dirt that really embeds well into the fabric, you get the surface dirt off, but the pressure drops are never relieved by vacuuming out plate filters.
You've tried that, Dave.
Tried it, measured it, don't work.
If you had higher humidity air, I would think the situation would be even worse.
Well, I suppose the filter would collect more junk if it was wet than dry.
Yeah.
You mean like an oil bath air cleaner in a car works a lot better than an oil bath air cleaner that's dry? Intuitively, I'd say that, but I don't know. Thanks, guys.
We should put up that formula again.
Okay. It's in the handout, but
Just backtrack a bit.
Dave,
yeah.
thinking of...
Welcome back, Roger.
Oh, thank you. I'm thinking hydronic-wise, we might be able to solve this. Here's my theory. If we solve it hydronically by having a bypass put on it, what would happen if you put on your high pressure side,
You mean,
two
yeah.
on your plan? Go back to your previous drawing.
Oh, sorry.
Between the return and the supply.
If you put a...
Which one, Roger? This,
I think he likes that one there.
Yeah, okay.
If you put a 1-inch tube from your hot plenum side,
for there?
From here?
from your pressure side,
Oh, yeah.
and bring it across and have a spade-type cutaway on the left side that injected air from the heating side, would it not break that turbulence smoothly?
Oh, hang on a sec. Hang on a sec.
Belongs to me here.
Do you want to deal with it, Terry?
No.
Okay.
It's not causing a monster.
Okay, just, no. What happens is, anyone who recirculates from a supply to return is an idiot. No offense. Because that appliance wants to see a quantity of air through it and cold air. If we spill hot air into return, the temperature rise can be still the same, but the delivery temperatures are now going to be rising more and more and more. We're getting out of the sweet spot for that appliance. It's especially critical in a heat pump, but it's not good for gas either.
Would a 1-inch tube be that drastically different?
Yeah, but you're peeing in the wind. So what if you return, oh, I see. You're trying to put it in a strategic location to try to solve this?
There or on the other side?
Well, you're aerodynamically a whole lot smarter than I am. Gary's a lot smarter than I am. What would you say, Gary? He's trying to break this problem by spilling a bit of pressure from the supply to prevent this.
And to make the air smoother going through.
Yeah, they use it in
Yeah.
airplane wings. What's it called? It's a
Instead of changing
spoiler
the
right on
fitting.
the wing.
Well,
Yeah,
no.
instead of changing your fitting, change the aerodynamics.
Yeah, I'd say no, Roger. You can inject air to make the air is coming out vertically, turn that corner, but it's going to require a lot of energy. You basically have to the energy in the air that we're blowing horizontally has to be
I think to answer your
strong
question, I
enough
think what you're getting
to
at
deviate all that.
is that unlike moving water where you're dealing with a lot higher pressures, with moving air, you could do it, but you need a booster fan.
You'd need way more energy than you have. You'd have to use half the energy you got to.
Well, you don't have enough pressure on your supply side to create the velocities that you need to do with your acid.
Yeah.
But they used to do, before they had the right appliances, like today's appliances, with any zoning system, we used to use the bypass.
In my opinion, and this is only my opinion, that a bypass is a nice clean method of selling zoning to get rid of that excess air that the zone can't handle. In my opinion, it's idiotic. It should never ever be done on gas furnaces, and much less never done on heat pumps.
Well, it's better with staged equipment.
Okay, now you're starting to add some intelligence to this. So if you are going to do it, knock down your source by staging.
Yeah.
But if you want to go hell-bent for lead and zoning, use a fan coil. We don't care what happens if you diminish the flow. But don't do it with compressors and don't do it with gas-fired equipment.
On high efficiency, there is another fan unit you can use. It's the Virgin.
Boy, I'm glad you're in the water side, Roger. You stay there, man. Yes,
We're
sir.
forgetting that air is compressible and water isn't.
No.
Hydraulic fluid.
No. Atmospheric pressure is 400 inches of water column, and we're running plus or minus a quarter of an inch in 400. You do the math. Air pressure and density and everything are linear with pressure changes from atmospheric. We have so much going for us right now in atmospheric. The amount by which your return is below and the amount by which your supply is over atmospheric is a quarter of an inch over 400, which is a friggin' small percentage. Don't go there.
I think that's his point. Any other questions? I'm sure David and Gary hang around if you got some other questions. And if you really want to learn this stuff in depth, do take the Basics of Air course if you haven't already. I encourage you to do that.
Just remember this formula, because you can apply this to any application. Anytime you want to check a different pressure drop across any appliance, you can just apply that. Read it out.
Is that a raffle ticket?
Yeah. I got one. Are we going to draw?
Yeah, no, not
Only
today.
if I win.
Well, maybe I've got the only one.
Yeah.
That's how you got the present, right?
Yeah.
No.